I'll officially start recording. Hi, Zoomers. Can you still hear me and see me okay?
Yes.
Excellent. Watch this. I'm going to share the screen right now and not forget. Yay me. We're at the point of the semester where it's important to have goals. My goals include remembering the screen share and taking a shower every few days, right? That's where we're at. We are at path analysis though, so thank you for sending me your homework 5 files. If you did not get it finished on time, no worries. You can submit it at any point between now and the end of finals week, and it's just 2 points off for being late. Doesn't matter how late you are. Revisions to that will be due at the end of finals week if you want to. If you look at your score and you're like, yeah, you can keep your point, I don't have time for this, that's fine. I'm fine with that. I am pragmatic and I realize that you have competing demands, and trying to negotiate which ones are critical and which ones aren't is a useful skill. There's a phrase I like about balls, like if you're dropping balls as like sort of a metaphor for being overwhelmed, you need to figure out which ones are glass and which ones are rubber. I like that one. It's like some things are just gonna get dropped. So if you don't have time to do a revision and you're satisfied with your score, I'm satisfied with it for you. Otherwise, the next item up for bids is formative assessment number 6. So I released that this morning. You should be able to answer most of those questions. And then homework 6 is a path model exercise. The TAs are in the process of helping me test it to make sure the answer key is coded correctly and that it gives consistent results across M+, Stata, and R Lavon, which is a non-trivial thing. But I had forgotten. So, Sora, you had asked the question last time, I think, can I use Stata? Yes, you can. I had totally forgotten that I set it up so that you could. So, and I
wasn't delinquent.
Yes, so I tasked the TAs with figuring it out in Stata to make sure that it all works. So it should be good to go. I will let you know once that's available. That will be due at the end of finals week as well. So you'll have about 2 weeks or so to work on it. Yeah, so I just this morning posted the rest of the materials for this semester. Woo! That's always a fun, like, this is the last of this is the last of that. So we have example 6A that we're going to start probably next time. I don't think we'll get far enough to be able to do it today, but in case I put it up. And then 6B and 6C. So these are all examples of path analyses. Each of them includes mediation as well. So another thing that folks would want to be able to do, and one of the main reasons people would fit a path model in the first place. So anything I'm forgetting or you have questions about with respect to our remaining workloads? No, we're good? All right then, get rid of that. So we're doing path analysis. Someone tell me what that means. Big picture. What's it for?
Boxes and arrows.
Boxes and arrows, yep, I will take that. Path models as diagrams are ways of depicting complex models that have multiple moving parts and lots of variables, yes. Path analysis as a procedure or path modeling as a procedure, those are synonyms. When would you want to do it? What's it for? What's it useful for? Predicting multiple outcomes, and I would call that what kind of model? Starts with an M. When you have multiple outcomes being predicted at the same time. Feel free to read from the screen too. Yeah, multivariate. Multiple variables, multiple outcomes. So path models excel at the situation of multiple variables. It is possible to trick univariate regression software into doing it, but it's a little more painful and it's not as flexible for generalized outcomes. When would you have to do it this way as opposed to trying to trick univariate software? There's one situation in which you cannot, univariate software is not going to work. Or at least it would be so painful to make it work that it's not worth the effort. Let's put it that way. One situation I can think of where you would want to do it this way. Has to do with mediation, this concept. Usually. No answers yet? I would say when a variable needs to be both a predictor and an outcome at the same time. That's when path models excel. What does a box mean in a path diagram? Or a rectangle, as normal people would call it. It's a variable. More specifically, is it real or pretend? It's real, yes. Things in boxes are measured, observed variables that are in your data set. Things in circles are pretend. They're either latent variables or they are error terms that have to be found after the model is fitted. So they're things you don't have direct access to, you put in circles. You will also sometimes see triangles to depict intercepts and means. I hate that convention and I rarely do it, but you will occasionally see triangles. What about single-headed arrows? What are they for? Directed arrows, or directed paths, as people would call them. I'll give you a hint. We've been doing it all damn semester, just not in a path model. Thinking of a synonym for a direct path that starts with an S?
And it's not an intercept.
Yeah, not an intercept, but a slope, yeah. So the vocabulary switches. What we used to call fixed slopes, we now call direct effects or direct paths, as opposed to indirect effects, which are combinations of slopes. Nonlinear combinations in this case because they're multipliers. We'll get into that later today. What's a two-headed arrow mean? Covariance, yes. So it's either a straight covariance if the variables that it is connected to are not being predicted. It is a residual or error covariance if they are being predicted. By the way, you can only have those in models where the outcomes are multivariate normal. If you have any kind of generalized outcome in your path model, there's a different way that you would let its residuals be related to those of another variable, and I will show you that in example 6b. What else? In these things, degrees of freedom have to do with people, yes or no? More new vocabulary. Degrees of freedom, is that a people concept or something else? Usually degrees of freedom have to do with sample size minus the number of parameters estimated. In this case, though, it doesn't. What does it have to do with? It's a switch from how we're used to thinking about it. Say it again? More generally, predictors and outcomes. So number of variables, yes. So degrees of freedom are based on the number of variables in your analysis. And for path models, this is a lot less of a thing than it is for structural equation models with latent variables. So that's the distinction in the terminology. Path analysis traditionally only has observed outcomes in it. But here's the handy-dandy formula. Number of variables times number of variables plus 1 divided by 2. That part right here refers to the number of possible variances that your variables have, as well as the covariances between every pair of them. The plus the number of variables at the end of it, this is slides 13 by the way, that is the number of means added back in. So in total, the number of possible parameters you can estimate in a path model has to be less than or equal to the number of means, variances, and covariances you have for your variables. And there were terminology that went with that. So what do we call it if we're trying to do too much? It's blank identified in all three cases. If we're trying to estimate more than we possibly can, what's that called? Under, just, or over-identified? Got one vote for over.
I don't remember what the question was.
You don't remember? You know what? That's fine. Thank you for answering. The question is, what is it called if we're trying to do too much? If we're trying to estimate more parameters than we have degrees of freedom? Yeah, this one's under. Yeah, it's backwards from how you would think about it. It's backwards. Yes. And that's why I'm making the point of this. I don't know who made up these names, but they need to be like punished because this is just confusing. So under is like you're underwater. Just think of it that way. Like you owe more than your house is worth. You're underwater. Just identified as like the Goldilocks and the Three Bears. Like there's the mama bear and the daddy bear and the kid bear stuff was just right in the story. So your model fit will be just right if it's just identified, but it means you can't be wrong. It means that your model has adequately, perfectly recreated the relationships in your data, so then you can focus on what they are, not the fact that you might have mispredicted them. Over-identified then, that's when model fit is testable. And the mnemonic I have for that is overlooked. You've overlooked certain pairs of relationships, so you leave some holes. So then the question is, did you miss anything you should have put in there? Because if you did, the rest of your results are going to be unusable, potentially biased by what you missed.
Whose fault is it? Who named these things?
I don't know whose fault it is, but it's got to be, I mean, like the path model rules were like published in the 1930s, I think. So like a long, long time ago. And even the identified, like that is not a word that is very helpful. So in practice, under-identified is broken. Just identified means you can't be wrong, and over-identified means you can be wrong, so you need to prove that you're not wrong before I'll listen to you. How's that? Shaking your head? Don't like the terminology? I know. All I can say is don't shoot the messenger, all right? But these are the terms. Like what I will say is like if I look at something that's under-identified, I'll say that's not even identified. Like under just like if it's under-identified, it's not going to work. Like you're going to get an error message instead of results. So that's the one that you'll know it when you see it. We walked through some of the rules for tracing these things. I don't need you to memorize these rules. I don't. And I'm not going to ask you ever, like in any class, to compute predicted relationships. The point that I want you to take with, I'll make this a little bit bigger here. The point I want you to have is that in these types of diagrams, just because there's not a direct arrow between two things doesn't mean that the model says they're unrelated. They are related in this sort of roundabout kind of way. So for instance, C and D do not have a direct relationship between the two of them, but they do have a relationship predicted by the rest of the model because I can go from C through the two-headed arrow over to B and then from B down to D as one of them. I can also go from C all the way over to A through the two-headed arrow labeled H and then down from A to D. So C and D are related through these two different pathways. The question is that enough to capture the full relationship that variables C and D have in the data? If it's not, then your model isn't going to fit well by the standards that we'll talk about today, and the rest of your results would be suspect, or sus, as the kids call it. Are we still saying that? Things are still sus? Okay. Are we still saying period? Yeah, we are? Okay. Anything else I should be aware of in the lingo? Help an old lady out. No? You're not going to tell me. You're just going to make me sound uncool.
Well, some aided recall would help.
Aided recall?
My entire brain just went blank of all the Gen Z lingo I could possibly know. So, it's not that I'm unwilling to help.
Mm-hmm. Well, it changes so quickly, too. Like, if I say, oh, that's sleighs, like, you'll probably tell me, we don't say that anymore.
They say gas.
What's gas?
Like.
How do you spell
gas,
that?
Like, that's really cool. Like G-A-S.
Oh, so is it a verb or a noun?
I don't know. I'm not sure.
Okay.
I think adjective.
It's an adjective. Oh, that's a gas? Like,
No, like that's gas.
that's gas.
I
Oh,
guess
fire.
that would be a noun,
Fire,
like that is.
okay. That's gas. So that's a good thing to be gassy? Because that is not what I would have went with that.
You said gas.
Just gas. Period.
Okay, that's gas. All right, I'll work on incorporating that into my vocabulary. Yeah, I've never been cool in my whole life, so why start now, right? That's my brand, is uncool. I still say things like, that's how I roll, which I am told has not been cool for decades, but I don't care, because that's how I roll, you see. So, not gonna make you memorize this stuff, but the idea is that we need to make sure that what the model says the data look like is what they look like. That's what we need to do. Otherwise, we're gonna be off in terms of our conclusions. I wanna do that. Okay, this is where we were. So how do we know how wrong we are? This is the steps of assessing what is known as model fit, which is how well are the relationships among your variables reproduced by the pathways that you've put in. If you put in every possible pathway between every pair of variables, you will have perfect fit and you don't have to worry about it. So for path models, that is often what I would recommend, because then you can't be wrong and you can just interpret your findings. Other people would call that cowardly, by the way. Yes. So like on the Quantitude podcast, they talk about that degrees of freedom are like your courage points, essentially. Like, because you're courageous in fitting this parsimonious model, but I'm not courageous. I just want to be right. So I'm okay with being a coward. When the model doesn't fit, we have to figure out why. So this is the idea of local fit, which is going to be looking at every specific pair of mispredicted relationships to see where the issue is. Once we have decent enough fit by adjusting the model as needed, we would look at the results and make sure they're all within bounds. So no predicted correlations above 1, for instance. And then the results themselves. How strong are the relationships? Just because my model fits perfectly doesn't mean I have anything interesting to talk about. So effect size is a logically separate thing. So continuing with our backwards interpretations of things, you get a hypothesis test as a chi-square as to whether or not your model fits. What that means is that the means, variances, and covariances in your data are adequately recreated by what is predicted by the model for your means, variances, and covariances. So this is an example of when you are cheering for the null. Okay? You want this test to be non-significant. And this is probably the first time that you've seen something like this. Because what non-significant means is that they match. What the data say and what the model predicts match. And that's a good thing. Because this is a function of sample size, though, most people disregard it and look for other ways of assessing fit. And there are 2 different ways to do this in terms of families of what are called fit indices, these various numbers that help you judge how well your model has recreated the data. Absolute fit is relative to the best possible alternative, which is called the saturated model. That's when you just say, hey, let the means, variances, and covariances be whatever you want and tell me how tall that makes my data. That's the answer key. That's the best you can do. So how much worse are you than that is a measure of absolute fit. The alternative is a little bit more cheerful perspective. How much better are you than the worst possible model you can have? So I like to think of that one as like my own sort of like personal reference point. You know, I know a lot of scholars that could make me feel very, very bad about myself. Like I don't know anything, I haven't published enough, I don't read enough, I don't work hard enough, because there's people out there that are writing, 72 papers a minute, and I'm not one of those people at this point. Vladimir.
Yes, a good question, Lisa.
Yes.
The null model had means and variances, but no covariances. Right?
That's correct. Yeah, I think, that's coming, I think. I hope it's coming. But we'll see it in an example if not. Yes, the null model is the worst model. That's where you give each variable its own mean and its own variance, but say they have no covariance whatsoever. That's like the worst thing that you could possibly entertain for these data. So to me, that's like relative to like high school graduation, Lisa, right? That's like the null model with respect to my field. Relative to her, I should feel pretty damn good about myself, right? I've done some things, I've learned some things, I've come a long way relative to null Lisa. Like, I don't know where saturated Lisa is, but like, I'm probably not ever gonna meet her. So, two different perspectives, which means that they will not necessarily agree because they're relative to different reference points. So here's one index of absolute fit, and here's your mnemonic to keep track of these. If the measure of fit has the word error or residual in it, then you want it to be small, because it is referring to how wrong you are relative to the perfect model, which is the saturated model. This one, the formula I can say in words more easily. This is how far off you are on your correlations on average. It's standardized so that it's readily interpretable. So if my SRMR is 0.08 or less is the commonly used convention, then the average predicted correlation in my correlation matrix is wrong by less than 0.08, like on average, which is pretty good in a correlation metric. There's also an unstandardized version of this, but nobody ever uses it anymore. RMSEA is root mean square error of approximation. So once again, this is relative to how much worse you are than perfect. This one is a penalty function. It is how far off you are in your predictions relative to degrees of freedom that are left over. So that means that it likes models that have more degrees of freedom left over, that are more over-identified, that are simpler relative in explaining the data. It will like those better. This one has a bunch of words that go with it. People disagree about what to label these things. Less than 0.05 is like the best you would hope for. 0.05 to 0.08, it would be considered adequate by some people. I typically don't try to label these, I just say what the number is. Like RMSEA is 0.09, you call it what you want. Like it is what it is. This one has a confidence interval around it, so you can get a sense as to how wiggly it would be in repeated samples of the same size. The smaller the sample, the wider the interval, as you would expect. And it also gives you a test of what is called close fit, which is less than or equal to 0.05. So this is a commonly used thing. Like it's a test of perfect fit is against the saturated best case model. Close fit is relative to an easier standard, 0.05 instead. So we'll see that in our output as well. Then the other family of how much better are you than the worst possible version, how much better are you than the null, is CFI and TLI. These are essentially the same thing. TLI came first, but it can go negative or above 1. So CFI was made to normalize it into a 0-1 range, and bigger is better. So you want these to be above like 0.9 or 0.95. So you're all the way better than the worst possible model, according to these things. Okay, so let me show you your first path models. How about that? This is part 2 of example 5. So these are the data collected from adult children, moms and dads. So family is the unit of analysis, predicting how conservative their attitudes are with respect to marital gender roles in marriage, from each person's education and also the gender of the adult child. So a relatively simple model conceptually, but it has a lot going on because of the multivariate aspect. So first thing that we have to do a path model is make sure our data is set up the right way. Fortunately, the data is probably already set up in the way that it needs to be. It's a wide data structure in which it is one row per sampling unit. And I'm saying it that way because, like in this context, a unit of sampling is a family. And the repeated observations, the multivariate outcomes on the family are the 3 people. So it needs to be the people in separate columns and one row per sampling unit in this type of data. So I have, in this example, I have Stata and I have M+, and I think, do I have R2? They're all running together in my head at this point, forgive me. Yep, I do. I got 3 different packages in here. I set a personal record with example 6A, though. I've got 4 in that one. I've got SAS too, but I took it out of the handout because it's just too much at this point. But I can help you no matter what software package you prefer. And I think even if you prefer one, it's good to learn others because you never know when you might need to do a special thing that only certain packages have, or you work with collaborators who only know one package and they want you to use it because they know it. So Vladimir has to learn SAS now, right?
Yes.
Yes, because he was fitting models in R that took hours and hours and wouldn't converge, and I ran it in SAS and it was fine in like 30 seconds. He's just like, oh, I guess I got to learn SAS now. Yeah.
We had a lot of information about how to proceed.
Yes, it also gives better diagnostics as to what's breaking the models, so. SAS is old school, nobody uses it anymore except me, but it's kind of like the 70s music that I listen to on purpose. Like, I don't care. I like my old stuff. All right, so in Stata, I am importing the data set in wide format that was pictured at the very front of this handout, this type of format here. So one row per family, separate columns for the gender of the adult child, education of each person, and then the marital attitudes outcome. So that's what it should look like. Yep, come back. There we go. In order to use M+, though, it requires a very specific type of data, which is text data, and no variable names at the top of the file. So if you need to make a file that you could use in M+ using Stata, here are the commands that you would need to do that. Export a delimited file, and this is what it would be saved as. I'm using comma-separated values as the format because then you can open it in Excel and see and have it look like a regular data set. So I'm putting in commas between columns. Replace means rewrite it if it's already made. No label means remove the variable labels, and no names means remove the names from the top row. In R, I'm doing the same thing with a command I found called write table, which I'm guessing is base R. Does that sound right? Yep. Yeah, no tidyverse up in here, just base R. So the data set I'm using is going to be this one, example 5 for M+. No column names, no row names, comma separated values, and then this is what it's going to become, this thing in green here. So if you need to make M+ data sets out of Stata or R, here's how you can do it. So here's the model that we are going to fit, and this is literally the exact same model that we fit in the first part of this example and left off on. So I'm doing that on purpose to show you the conversion between the two. So in this version of the model, it's on long format data where each person is in a separate row. So that's why we have the two subscripts, F for family and I for which person in the family. This is the version that has outcome-specific fixed intercepts rather than a general intercept. So note, like these three first terms right here, those are intercepts. They don't look like it, but they are, because there's no beta 0 that's all by itself. So you can think of this as this is the dad intercept, this is the kid intercept, and this is the mom intercept, because each of these is a dummy code that turns on to a 1 when it's that row of data and a 0 otherwise. So these act like switches to essentially turn effects off, on and off across the rows. I have the effect of the adult child's gender on their own attitudes, and then I have the effect of everyone's education on their own attitudes, each person's education on their attitude, actor effects as we would call them. And then I have dad's education on the other people's attitudes because that's what the research team was interested in. So as a path model, let's start with Stata and we'll work our way through the other programs. So I am using the Stata package SEM, which is for multivariate normal single level stuff. It's older, but it's fine for what we have here because we're pretending all of these things are multivariate normal. I am writing out more things than you would need to write out so that you can see how you could request customization to the model and also for transparency. Like this is all the stuff I'm asking for at the same time. So note these extender lines, okay? This is a pattern that is very easy to screw up. When you see 3, that means keep reading, keep reading, keep reading, keep reading, keep reading, keep reading, until you get to 2, in which case don't keep reading, that's just a comment. So it looks like the same. Like if you weren't paying attention, it would be very easy to miss, and I've screwed this up on too many occasions, so I'm making a point of saying it. So I'm entering comments out here, but the 3-line combination means keep reading, keep reading, keep reading. So first line here, I'm asking for intercepts for all 3 of my outcomes. So underscore CONS stands for constant in Stata language. Note that you can have the arrows go this way or the other way in Stata, but I'm writing it this way to stay comparable to M+, which does not have that flexibility. Can you guess what it would look like if you wanted to change it around? Rather than a less than sign, it'd be greater than. So, yeah, you get it, point being. So these are the outcomes, these are the predictors. So I've got 3 intercepts. I've got the kid outcome being predicted by 2 things, their gender and their education. I've got the mom outcome only being predicted by mom's education, but then dad's education is predicting all 3. So note that in all of these packages, you can streamline your code to have multiple predictors on one line and multiple outcomes on one line. So if I wanted everything to predict everything, I could just put all the outcomes on one, all the predictors on other, and it would write multiple equations at the same time. So just this much is writing 3 separate regression equations predicting each person's outcome separately. Okay, with me so far? All right. Other things that I'm asking for, var with an E in front. Those are residual variances, error variances, leftover variances. I also, because these are people from the same families, they need to have covariances. So this is what makes the model address the dependency. Remember that word? Dependency means correlation of outcomes from the same sampling unit. This is how I'm addressing it. I'm literally telling the model, hey, let the outcomes from the same family be correlated, okay? And because it's multivariate normal, it's like, sure, go right ahead. If this was a logit model or a log model or any other kind of generalized model, I couldn't do it this way. So stay tuned for that. So that part so far is just the model itself. These are all the things that are going to be in my model. Next up, 2 lines. So now we're getting into the options and additional pieces of information. Method MLMV means full information maximum likelihood. That would be used if you have missing data so that it doesn't drop cases that have missing information. In Stata, it brings everything into the likelihood. So if you do it this way, it's treating predictors as if there's outcomes without you getting a choice on that. Next up are some examples of linear combinations, differences between slopes, because why not? The only catch is that you have to figure out what they're called internally. So lincom you've seen before, right, Stata folks? That looks familiar? Linear combination. And then we get underscore B open bracket mom marital colon dad ed 12 close bracket. That is a very long way of saying this is the slope of dad's education predicting the mom's outcome. How the hell did I know that? That's a reasonable next question. This option right here, SEM, coef legend, that prints a table with the labels that it uses internally for every single parameter so that you know what they are and can access them. That, I believe, is a more general option that shows up in all the Stata routines. Coef legend is something you can add and it will make that table for you. In addition to the unstandardized solution, I want the standardized solution, which turns all of the slopes into a correlation metric instead of a regression scale-specific metric. GOF, any guesses as to what that stands for?
Global fit?
Global, I don't know what O is in that case, but I think goodness of fit is how they talk about it. When I first heard that term, I'm like, people do not really say goodness, do they? Yeah, they do. That's a thing, goodness of fit. And which ones would you like? All of them! Here's 2 extra pieces of data that are provided by default and the other packages that were not provided, actually 3. So I had to figure out how to go find those. So what is the log likelihood for the H1 model? That is the most perfect model that you can have. What is the number of parameters that you're estimating? That's something you would want to know. So make sure that it's reading your code correctly. And then -2 log likelihood in case you need to feed that into something as well. EQ GOF, that is R-square. I don't know how EQ GOF turned into R-square, but I didn't make it up. Residuals, this is discrepancies. So this is not the idea of residuals as you're used to thinking about them, like the e's at the end of the regression equation. What they are is a match between the variance-covariance matrix that's in your data and the one that's predicted by the model. These are how far off you are in each little spot. And then we get into, this is the old school version, yes, old scale, I'll go with that, of ChatGPT to fix stuff. When you don't want to write something, right, you just like pull up ChatGPT or Google Bard and put in a prompt and it's like, can you just fix this for me? Sure. So this stands for modification indices. They are score tests that tell you, hey, you know what? If you add this parameter, your chi-score is going to be better by this much.
Is this new as of this class, or
Nope.
did you talk about this last time?
I think I added the joke this year, but I've talked about modification indices before.
Well, right, but in Stata, I'm wondering if this is new in Stata. I knew they were a thing in M+.
Not that I know of.
Okay, well, I'm just a bad listener.
You mean you don't recall every word out of every lecture I've ever given over the last 3 years perfectly?
That's the real reason why I'm TAing for you, is just so that I can rehear the lectures.
Well,
You're just re-going.
yeah,
going over
you're
everything.
re-going over the entire course content. Well, the thing is that it is unrealistic to expect yourself to know how to do something accurately the first time through. Like, this stuff takes time to sink in, right? T's sitting here of her own volition, even though she's familiar with some of this. It takes time, right, Vladimir? This is what, the third time you sat through this?
Yeah.
Yeah. But this number right here is, hey, what's the cutoff for what I'm going to show you for your cheat code to fix your model? This is tied to a chi-square, where 3.84 corresponds to a significant improvement in fit for 1 degree of freedom at an alpha level of 0.05. So that's why that number is there. You can change it to make yourself more conservative. And show P class all means I'd like all of them, please. There's choices there. So I liken these to like cheat codes. Like when my brother was younger and he got his first Nintendo at like age 10 or something, that was the happiest I've ever seen him in his entire life. Up until the Chiefs won the Super Bowl a couple of years ago for the first time, that was a close second. But the Nintendo was like his lifeblood. And back then the games were hella expensive. Like they're still really expensive, but they were the $60 then too, like 30 years ago. So that'd be like $100 now. But one of the things that he did to improve his game was buy these magazines where they would tell you like where the hidden stuff was in the games. So he could finally beat the game, you know, that he paid the $60 for in like 3 days, because why would you work for it on your own? So that's what I think of it. Like these are the cheat codes to help you beat the game. Doesn't mean you're a good gamer, just means that you beat the game. So these are completely atheoretical. You would only want to listen to them if you can rationalize them and defend them in your discussion section. That's the guidelines I would go with. But we're going to look at these as part of the evidence as to how we diagnose a misfitting model. Okay, I know that was a lot, but most of what I said is written down in comments. The full results are available in the zip folder that goes with this example. Questions or things you want me to say again?
How did you get the number after the cheat codes? The number, the
This
3 point, yeah.
That is the critical value from a chi-square distribution, which is the unit of test statistic that we have here to improve model fit at an alpha level of 0.05 for 1 degree of freedom. So basically it's like, only show me things that are going to significantly improve my fit if I added each of them.
Okay.
All right, other questions? So here's my output. I have 140 observations. That's the number of families. Because in this, it's a multivariate analysis of the family as the sampling unit in this case. First thing it tells me is the log likelihood, so the same as Stata results would typically give you. I have a note, though, that this is not going to match M+ because of the difference in missing data. So it brings all of the predictors into the likelihood. I didn't have to do that in M+ because there wasn't any missing data. So that's why it will not match, but the rest of the results will be the same. Then down here, we get unstandardized solution. So what that means is in the metric of the original variables. So a 1 unit change in X per 1 unit change in Y, that kind of thing. Then we get a separate regression model for each outcome. So this kind of looks in structure like we had in the ordinal and nominal unit when you had the submodels and you had the slopes for each. Like these are different boxes that are being presented, but it's the same idea. Stata still puts the fixed intercept at the bottom of each of these columns against my will. So that's the last thing in each of these lists. But for instance, kids' attitudes is predicted by their own gender. So boys, adult men, are more conservative than adult women. Non-significantly, the elder child who is more educated will be less conservative. Older children who have dads with more education will be less conservative, but non-significantly as well. Moms who have more education are slightly less conservative, not significant. No effect of dad, and then dad's education on his own outcome is significant. That more conservative means less education, or other way around, you say that. So this is organized, I think, in a way that is readily interpretable. It corresponds directly to the idea that we have no general intercept in the model, but each person gets their own. So this is like the beta 0 times the dummy codes part. And in fact, this is what I did for you. So in this last column here, I did this. This is not Stata. This is me saying where the parameters correspond in the linear model version of this equation. So there's a one-to-one mapping for all of these things. So those are the slopes that I care about. Also, I have residual variance, so variance is left over for each of my things, which you would find in the R matrix on the diagonal. So that's what the UN11 means, the unstructured R matrix, because we didn't put any constraints on it. And then the covariance is among the three. So these are the residual relationships. Attitudes are still correlated across family members even after you control for education and adult-child gender. Likelihood ratio test of model versus saturated. This thing right here is my model perfect? This is the one that we want to be non-significant. And lo and behold, it is, but that's a little too close for my liking. Then after that, we get the examples of differences between slopes using LinCom. So this is asking for a comparison of the effect of dad education, for instance, on mom and versus kid outcomes, kid versus dad, mom versus dad. It is one slope minus the other. And here's the table that follows that COEF Legend generated that tells you what each of these is called according to Stata. So that's where I got those names from. And they do have to be case and space sensitive from what I remember. So lots and lots of output from these models. Standardized solution takes all of the variables and transfers their means to 0 and their variances to 1. So then these things are in standardized slope metrics instead. Let's see here. Here's more GOF. So here's my goodness of fit. And this is the one instance in which it did tell you what it means. So this model versus saturated, Stata wrote that in the output. So then I have my notes out here. These are notes from Lisa out here. This is more specific. So this is the test of whether our model is different than the best possible model. Ours is called HO. The best possible model is called H1. The second one, you can always ignore. This is asking about the difference between the best model and the worst model. It has nothing to do with your model. After that, we get into the rest of the fit statistics on page 14. So RMSEA is 0.077, which would be considered acceptable-ish. It is not significantly different than 0.05, which means it has close fit. AIC and BIC are in smaller is better form, but they don't match M+'s results either because it's using a different likelihood function. What about CFI and TLI? 0.87 and 0.68. Good enough or not quite good enough? Not quite good enough. So even though our model is not significantly different than perfect, it looks like there's a little bit of room for improvement still. And let's see, size of residuals, SRMR. That one's pretty good. And coefficient of determination, I have no idea what that's supposed to be. That's a Stata thing. So there's no standard for that I'm aware of, at least. R square. So note there's only 3 variables in here in the R square section. How many variables are in my model in total? I've got 3 educations, 3 attitudes, and 1 gender variable, so I've got 7. Why do I only have 3 variables in this table for R square? Cough, cough, homework question. Question from the Zoomers, do we need to report CFI and CLI or just CFI? I'd say it depends on how much room you have, ideally both, but if not, then CFI wins over TLI since it's standardized. TLI is also called NNFI by other places. But my question is, why do I only have 3 R squares here? Cough, cough, homework question. TAs, what do you think? Why do I only have 3?
You take this one.
Because those are the variables we are treating as outcomes in our model.
Yes, these are the outcomes. These are the endogenous variables that are being predicted. We are not predicting the other ones. So what would their R square be? Yeah, 0. If it's a predictor, it has all of its variance still to be explained. So we have okay fit by some standards, room to improve by others. Next step is to figure out what the problem is. And I do have a real world analogy for this one. Let's say that your children come home someday with a report card that says they have a B average, a 3.0, across their courses. That's not bad, right? But let's say that you're the kind of parent that thinks that's not quite good enough. The question would be, did you get a 3.0 average by getting 4 Bs? Or did you get 3 As and an F? Because there would be very different solutions for how you might improve your GPA under those circumstances. So that's what we need to figure out. It's like, is the whole model like off a little bit everywhere, or is there like a local problem that's causing most of the offnesses? Is there a course that the student would need additional tutoring in or something? And is that course PE? Because if so, you're fine. I don't care if you fail gym. I also don't care if you fail art or music, or any other thing that you don't want to do, but I will care if you fail math, of course. That's how my son is going to rebel someday, is that he's going to become like a qualitative researcher.
We'll welcome him in social.
Yeah. No, he doesn't like music and art, he tells me, so that's why those two come to mind. I'm like, you know what, fine. You don't have to like those things if you don't want to, but maybe someday you'll change your mind. So now we're trying to figure out like where the hole in the GPA is. And the pieces of information that we have to work with, this is the residual section. First off, we have mean residuals. What these values represent is relative to the mean of each variable and relative to the mean that is predicted by the model, how far off are they? And you'll note they are all exactly 0, and that's not a coincidence. Each outcome got its own intercept, so its mean would be perfectly reproduced. The predictors were not even trying to reproduce. They just get means and variances as part of this, so they can't be wrong. So we know that there's not a problem in reproducing the means of the variables. Likewise, down here is a covariance matrix of offnesses. These are discrepancies. And the diagonal is mostly okay, but just a little bit off. And that would be not unexpected if a model doesn't fit well, but because each variable got its own residual variance, these should be pretty much okay. I've highlighted the ones that appear to be responsible for the biggest problems. In particular, mom education with dad marital. There's no slope in the model that directly connects those two variables, and so the expected relationship is 0. The actual relationship is negative. So dads who have married more educated moms are less conservative. So it looks like mom ed is what's causing the misfit in this case. So we controlled for dad's education, but not mom's education, and this is indicating that we should have done so. So this is additional information, this idea of fit and diagnosing where you're wrong, that doesn't happen in regression software. You would have to do a whole lot of extra work to get this information out of it, so that's another reason you might prefer path analysis. And what do the cheat codes want us to do? It wants us to have mom, let's see, mom education, predict dad marital. And it wants mom marital to predict dad marital. Well, that can't happen. They already have a residual covariance. So these things aren't even always logically possible. It's just trying to fix it. But this is the one that we would definitely want to have. Okay. How are we doing? Yeah, we're doing. That's what we're doing. We're surviving. That's good. R, folks, here is how you would do it in Lavon, which is far and away the most common package for using SEM in R. I actually don't hate it. It provides organized output, and the code makes sense to me. However, there's certain things that are completely backwards relative to M+, and I'm not sure why they did that, but it makes your head hurt a little bit. You also need to make sure you can locate the squiggle key on your keyboard. It's called a tilde. Mine is above the tab on the left-hand side. Squiggle is a very important character in SEM and the Lavon package. So the way this works is essentially you write out your model, save it as an object, and then tell it to reference that object when you call the function for Lavon. So all of this right here is one thing, and it's all in green because it's being saved as a text string, which in my version of R renders it all green. But I think that's something you can change probably. So I'm listing out everything that's being estimated. So squiggle squiggle is how you tell something that has a variance or a covariance. So putting the same word on both sides of the squiggle squiggle means you're asking for a variance of that variable, a residual variance for leftover information for this case. Same thing with moms, same thing with dads. Note I had to put semicolons in between because otherwise it thinks it's one idea per line. So this makes it so that you can write multiple things on the same physical line of code. Also this one, this is how you tell it I would like covariances. And the plus sign is not literal addition. It just means add this to your list. So kid marital has a residual covariance with mom marital and dad marital, and then mom marital has one with dad marital. So putting different variables on the sides of the two squiggles generates a covariance relationship, a two-headed arrow. Intercepts are squiggle 1.
I have a question
Yeah.
about that. Because M+ you can just put them on either side of each other.
Yep.
There's no way to do that.
I do not think so, but I'm not 100 on that. Vladimir, do you know?
Well, what?
So in M+, you can have like a stack of variables and then with and then a stack of variables to have them. Can you do that in Lavon?
I don't think so. But
Okay.
you can have one term and then add other things with the plus sign.
Yeah.
Yeah, so I did that
Exactly,
here.
but
But you couldn't put a plus sign and other things on the left-hand side?
I don't think so.
Okay, of course not. Yeah, all right. Well, I've never tried it, or I tried it and it didn't work and I forgot about it. One of the two. It's possible. Regressions are single squiggles where it is y on x. So we have the y side is first, and then the squiggle is like an equal sign, and then what are the predictors then come on the right side. So kid marital is predicted by two things, mom marital is predicted by one thing, and dad marital is predicted by one thing. Where do we get that? Yep. There we go. One thing. These things in parentheses, these are labels. They can also be constraints where you can tell it to make multiple parameters be the same, but in this case they're just labels. And what they are used for is to be able to do math on any parameter in your model. So for instance, I have labeled the slope of dad's education predicting kids' attitudes as this word right here. I've labeled the slope of dad's education predicting moms as this one, so 2K and 2M for 2 kids and 2 moms. I can then down here with colon equal, so not squiggle this time, different, do linear combinations. So this is like lincom. It's like GLHT in R. What I'm asking for is the difference between those two slopes, and I'm taking that difference and giving it a new name. So colon equal like that is how you define new parameters out of existing ones. Linear and nonlinear combinations, and they can be nonlinear as well. So within this, I wrote out everything that would be in the model. The only part that you really have to specify is the regressions and the residual covariances. Then we've put it in to the Lavon function. So we tell it what data, what syntax, what estimator. So I'm using robust estimation so we can compare regular and robust. Mimic equals a bunch of defaults that it takes to make it look like other packages. So I put that in there just in case. Then I'm asking for additional information out of the summary. I want the fit measures, R-square, standardized solution, and confidence intervals as well. Mod indices is a function then that you take and request out of the path model saved object, and I can tell it what the minimum value is for these. And then the resid function gives you that discrepancy matrix, so you can see how far off you are for each of your spots. And I don't have that output here, but I've got it later on. So I tried to like give you some of each. Yeah, this is M+ output. Okay. So folks who want to learn Lavon, any questions about any of that? All right, then here's welcome to M+. Ta-da! So M+ is different than other packages in that you can't have more than one model in a file. It reads the entire file from top to bottom. You would have to literally comment out anything you don't want it to read. So this set of code here would all be submitted as one model, like the whole thing is just one file. And if I wanted to make a separate model, I would have to make a separate file with the separate model. And so you get into what we call file hell very quickly with this. And you have to come up with naming systems that work. And if you're like, yeah, I don't want to play in file hell, there is an R package called M+ automation that helps you keep track of things. And it will read things, or it will write things, read things, bring it back, and save the results as R objects. So Vladimir's doing an enthusiastic nod at the back of the room.
Yeah, it's helpful.
It can be very helpful for that. I have not played with it as much, but I can see the utility. The other thing, as I have at the top of this, you can only have 90 characters in a line of code. It will quit reading after that. It also requires line terminators of semicolons. So everything you do needs to have a semicolon at the end of it. In M+, comments are started with exclamation points. So that's like this, can list the file name of the same folder, that's a comment. So I try to annotate my code with what the lines are supposed to be doing. So it wants to know where your text data is. If your program, this file, is in the same folder location as the data, then you can just list it like this. Otherwise, you need to write the whole entire path to find it. We're taking free format data, so comma separated or tab delimited would work for either of those, and individual level data as opposed to matrices for input, that kind of thing. Anything in blue is a recognized M+ command. Anything in black is text that you would potentially change. So the data section, then we tell it where the data is, where the data file is. Under variable names, this is where you tell it what the order of the variables are in your file. And it has to be exactly right. So I would highly, highly recommend subsetting your data down to just the columns that you need so that you don't have like 500 variable names listed out here for you to potentially make an error and have it go wrong. Use variables then further subsets the data into just the ones you're using. And each of these, by the way, each of these names can only be 8 characters or fewer. It's old school. You want to tell it what kind of missing data codes you're using. I put -999 is usually some permutation of that in my examples. Type equals general and estimation equals maximum likelihood. That's what we're using for our standard path models. Confidence intervals we can ask for. Standardized solution we can ask for. Residuals, discrepancy matrices we can ask for. And then mod indices are the cheat codes. And again, 3.84 is the chi-square value that corresponds to 1 degree of freedom at an alpha level of 0.05. Residual variances in M+, you just list the variable. So if you see a variable's name just listed, that's referring to either its residual variance, if it is being predicted, or just its variance, if it's not being predicted. This is what we were just talking about a minute ago. So I have a stack of 3 variables, and then the keyword with, and then the same 3 variables afterwards. With means covariance. So 2-headed arrows are withs. And this gives me all possible combinations. You don't have to write each covariance separately. When you see a variable in brackets, that is either its mean or its intercept. It's its mean if it's not being predicted, it's an intercept if it is being predicted, and it knows, based on the rest of your model, what it should be. Then finally we get to the part that turns it into an analysis, on. On is a slope. The order of this goes y on x. I think of on as an equal sign, because when we write equations, the y's are always on the left and the predictors are always on the right. So this is an example of how you can also stack up slopes. So I have 2 slopes predicting the kid outcome, 1 slope predicting the mom outcome, and then 1 predictor having 3 slopes for 3 separate outcomes in this case. And in parentheses, just like in Lavon, those are labels. So I'm naming these slopes so that I can do math on them. In this section, which is called model constraint, I am making 3 new terms that are going to carry the differences of the slopes, and those will show up on my output. So model constraint with the new command is the analog to GLHT or lincom to define linear or nonlinear combinations. Question, will the mod indices always stay 3.84? No. If you wanted to make it more conservative, for instance, I think, what is it? It's closer to 6 at an alpha level of 0.01 for 1 degree of freedom. So you can make it more conservative if you wanted to have less chance results pop up. That would be a reasonable thing to do. All right. Here's the same information in a different order that we got out of Stata. What M+ gives you first is fit. It doesn't even give you the results until you have to scroll through the fit section. So it's making sure that it's like, no, do not pass go until this part is okay. We have our model's height versus the perfect model's height. And then we get 10 as the -2 log likelihood difference. So this is a likelihood ratio test, this chi-square. The fact that the p-value is 0.09 means that it is almost not worse than perfect. It's all right on the border. 6 is degrees of freedom. That means how many things we left out. So let's go to the picture and see. What did we leave out? I've got child sex predicting their attitudes but not the other 2. So we evaluated that already. Child education is only predicting theirs and not the other 2. So that's 4 more. And in this model, we do not yet have those 2 paths from mother's education. So there's the 6. Note that none of the relationships among the predictors are included with respect to M+ because they're being treated as predictors, which means we don't worry about their summary statistics in these models when they're only predictors. They're exogenous, is another word. So that's where the 6 came from. Can we draw a figure like this in Stata? Yes, Stata has a diagrammer. Does Lavon have a diagrammer? You guys played with that at all? No?
Maybe.
M+ has a diagrammer,
Yeah.
but it's a relatively new invention. The story goes that when M+ was created, they hated the idea that people could just draw pictures and like not write code and run analyses that way like Amos has and EQS has. So they were never going to have a diagrammer. But then their head programmer's 13-year-old kid as a class project made one. 13 made the M+ diagrammer. I heard this story at a workshop, and they were like, it was so good we had to keep it. So now M+ has a diagrammer because this kid picked that as his class project. Talk about comparing yourself to the saturated model, right? Like, okay, I quit. Like, I can't beat a 13-year-old kid because there's no possible way I could have done that coding, but he did. So, anywho, we had 6 degrees of freedom left over for that. And there we are. back to the 6. So then the rest of this RMSEA is not significant, meaning that it's not different than 0.05, which is a good thing. CFI and TLI are not quite good enough. SR/MR is okay. And then here's the results. These are the unstandardized results. So the on statements, these are all slopes. The with statements are all covariances. And once again, I labeled each parameter as to what it would be in the linear model representation. And then last but not least, these are the new parameters. These are slope differences. So these are differences in unstandardized slopes across the outcomes. So for instance, if I look at this one, that one is saying that dad's education has a bigger effect on his outcome than on the kid's outcome. That's what it's showing. Then we have the standardized results, which are more commonly depicted in path model diagrams as well. All right. And then the same residual information in terms of what is missing right here. These are where we're off in terms of explaining fit. And modification indices to be able to, for suggestions to help it. So it wants mom and dad marital to have a slope between them. We already have a covariance, so it can't do that. It does want mom's education to predict dad's marital, and we can do that. Oh, and Vladimir just found a diagrammer.
That's a package.
It's a package.
Yes.
Of course it is. I should have. It's another 13-year-old probably wrote that package as well.
The thing is that you need the specifications, the inputs, put them manually. So good luck trying to
Okay.
put all the numbers and things.
So it's not going to be an easy package to work.
I don't think so.
Yeah.
But you can use it if you need a graph.
Yeah, I usually draw my graphs in PowerPoint. I don't like fighting with the diagrammers. They just make me mad.
Yeah.
And then I just have to figure out how to make the curved arrows, which is my nemesis. But there's a lot of different visual display packages that you can use to make path diagram type things. It's just that getting the numbers back on them is automated in these SEM packages in a way that makes it more convenient. All right, 311. I think that's enough for today, don't you? I think yes. Yeah, I think it's enough. Any questions before we call it a Tuesday? Okay,
Can I ask a question?
yeah.
So you showed us how to use R, theta, and M plus with
Yep.
for the path analysis. So personally, what do you prefer? Which one you think is better, and then why?
It depends on what else I need it to do, but M plus has the most flexibility overall for different kinds of models. I would say that Stata's GSIM package is a close second, but it handles missing data in a different way that is less optimal. Lavon is much more limited. It doesn't have, the only link functions that it has are for binary and ordinal. It doesn't do any other kind of outcomes, and so it has even less flexibility than the other two.
Got it. So homework 6, we should choose M plus.
Well, since you already learned how to use M plus in the other class, that would be ideal to capitalize on all your new knowledge. But if you want to challenge yourself to learn something new, then maybe Lavon would be a reasonable second choice if you're going to continue using R.
Got it. Thank you.
Sure. All right, then how about we wrap things up for today? Finish the last model next time and start another path analysis journey. Thanks for being here. You can go now. It's okay. They're like, we're just shell-shocked. Thank you. Bye for now.